Here's the Fourier transform graph from our from that 300 hertz tone that we just recorded. Now it's important to note that this is normalized between, the values are normalized between 0 and 80 because, you know, the drone's going to be flying this path and, you know, I don't have infinite space in this basement. So now what you're going to do is send these as a series of coordinates to the drone in order to have the drone fly these out and show to just the general audience what the composition of the signal looks like. Right, so uncomment this. This is what actually sends the set points to the drone. And gonna take off in 3, 2, and 1. Right, now we're going to send some set points. Again, moving along with each point on that Fourier graph. So once it hits 80, then it's going to go back to the origin and then land. Or I'm going to land it. See, it's hit 80. Now it's slowly going back. Just to, you know, avoid it darting quickly when I land it. What's also important to note is that since we have the magnitude, the frequency, and the phase angle, which was calculated separately as the arctan of sine over cos or imaginary over real, we actually have all the elements necessary to generate the sine wave ourselves. So if, say, a user, someone wants to see the full sinusoid, that being at 300 hertz where magnitude is greatest, we can actually fly it out for them too using the drone. So here I've substituted the normalized x and y for the x and y of the generated sine wave, which we now send to the drone as a set of set points for it to fly along. So again, once we get it started, and then send it some set points. You can see it flying the sine wave, moving periodically. Should note also the frequency is normalized between 0 and 100, so it isn't exactly 300 hertz because that would just kind of look like an incoherent mess. And reaching 80, you can see it traveling back, and you know, we're just going to land it a bit early.